All right, let's get started. Good morning. We have a leaner class today. Yeah.
Do we have an exam on Monday?
Yes.
Okay, just making sure.
Yeah, we have my exam on Monday. Yeah, so pretty much we're kind of at the end of the lectures, right? This is probably the last but one lecture, right? So I want to kind of tie these things together because, there's probably the notion of operating system where it came from. There's probably what we kind of looked at a number of different technologies, and probably the notion of takeaway message kind of stuff, right? So I don't know how you feel about what you learned and all those things. And my sense is whatever you do, you're going to bump into operating systems all the time, whether you like it or not, unless you don't want to do any sort of programming, unless you don't want to use any computers, right? Otherwise, you want to sort of understand what's going on. Like, for example, when I logged in, it takes a while for me to log in, right? It keeps waiting for things to happen. And you like to know that's because some pages are being brought in or something, and somebody says, how would you fix it? You will have to have some sort of maybe more memory or something like that, right? So that's sort of, so it's going to come with you whether you like it or not, right? But in terms of what we sort of looked, right? So are there any questions about anything we covered so far before I kind of try to look at the big picture, any of the technologies, right? Security for the exams, you'll only will only be asked the very minimal stuff I covered in class, right? Not the network security, encryption, all those things, because that's way above the scope of this class. We never looked at any distributed systems because that's best dealt with a separate class by itself, right? So there were two things we sort of looked throughout the class. We looked at abstractions. Some of them might have been new, some of them you probably used before. And we also looked at ways of implementing those abstractions. So you can kind of know how those different abstractions are implemented. And the idea here is once you understand how the abstractions are implemented, then you will try not to work against those abstractions. You need to understand how these things happen. For example, if you know that things are implemented in a block level stuff, like block-based file system, then certain things, if you could help it, really matters. If you're sort of building a database or something, right? They worry about those. They try to keep the stuff in the block boundaries, so you don't have to read two blocks, you don't have to write two blocks and things of that nature, right? So that's what we want. So and most of the implementation stuff are affected by the hardware, right? You have a memory management unit, and it does certain things, which lets you do virtual memory and things of that nature. And the hardware wants to do what software can use. So hardware wants to come up with dual core, software wants to come up with threading, and we are sort of in the middle trying to manage both those stuff. So hardware defines what you can do, and software defines what hardware can use, and that's important to understand, right? If the hardware cannot do something, we can't do magic. If the hardware has certain cost, we can't do magic, right? One of the examples is if it takes you 10 milliseconds to read a hard disk, we can't do anything for the first time. We can do the second time, we can do caching and all those things, but the first cost you still have to pay, right? So the abstractions we learned, which are sort of what you want to take away, which is like sort of introduced. The first is the notion of processes, right? How many of you knew what processes were before you took the class? Actually, the answer should have been everybody, right? Because when you wrote a program, you should have, right? But the point is, you'd use something which you never thought about what was being done, because when you wrote the first Hello World program, it was abstraction. But probably you were never taught this is like a process abstraction, and it has this PCB and all those things which implement those things. But it was already there. We're kind of saying the stuff that you should have known, or you used all your time. This is what it really means, right? What you may not have learned is the notion of threads, right? And which was brought in because of the notion of you have multiple processes, how I would give that to you, right? And at that point, our operating system stuff was over, but it turns out that if you just have threads, you run into a whole bunch of issues with deadlocks and all those things. We had to develop these notion of semaphores and locks and stuff to solve the problem that we created, right? So the first two modules essentially, if you look at it in a very flippant kind of fashion, processes you already know before. I'm just telling you how it's implemented. There's like this scheduling and all those things. But hopefully this will clarify what you did in your programming class, right? The other notion is the notion of memory, right? you knew memory all along. I mean, that's the first thing you did in your C program. Your hello world printed a string, and that's in memory somewhere, right? And you probably didn't have to learn anything more about how to use memory from this class, right? But we introduced the notion of virtual memory and all those things internally to implement things different ways and do all kind of nice stuff, right? Does it matter that the application knew about virtual memory, logical address or physical address? Let's go with the logical address, right? Did you have to know about logical and physical address to use memory? Do you have to know? Do you think you need to? Do you need to know? Right, because when you use a C program, you just create a variable. You don't care where it is, right? But knowing that this virtual memory and all those things would potentially help you in writing your code certain ways. Knowing that this is how things are arranged would help you build certain things, right? And we'll see how that might help in different scenarios, right? And then the notion of files, right? Again, we didn't introduce files here. You used files before, right? That's part of your earlier courses. And what we're trying to learn was, when you talk about files, what you really meant. You want something persistent. So naturally, you had to get this notion of directories and how to store them, right? So we learned the abstraction and the implementation. Abstraction, you sort of knew from earlier. Maybe you didn't think about it as much. And now, hopefully, these things are there. So even though it looked like we went through fairly 5 different modules with all kind of concepts, right? If you look at it, it's reinforcing what you did, right? What I don't want you to take away from this class is there's a bunch of technologies that you kind of learned, and they were kind of floating around in midair, right? They all kind of should have reinforced what you did in your programming class, and they'll be reinforced again when you take higher level classes, right? Does that sort of make sense? Right? And there's notion of protection and security, but we didn't go too much into that because protection is something that we can do something about. Security brings up a whole bunch of different aspects that we don't have to focus. They're important, and you'll read them in higher level courses when you take them, right? And again, to reiterate, when you talk about implementation, right, we knew processes, or we kind of knew that they kind of existed, right? And implementation-wise, we looked at PCBs, how to create them, how to destroy them, how to schedule them, right? So one of the things that is kind of throughout the system is the notion of scheduling, right? Scheduling resources for getting good performance. In terms of processes, you want to schedule the good process versus not so good process. You want to look at memory. And again, the notion of logical and physical helps the operating system in managing stuff for you. Not necessarily what the program wants, but it does a whole bunch of nice stuff, right? It lets you run programs bigger than how much physical memory you have. It lets you run lots of more programs than what you would have. And so those are tricks to get the most out of the hardware you have. But in terms of your programs, this is no different than what you did before, right? And we'll be successful if I can do these games and still makes you think like you're using a machine which is useful, right? If these things slow things down, then you'll be unhappy. And the notion of directories and files, which you knew files before because when you had to open, you had to do the stuff. You probably never had to worry about partitions and all those other details that disk scheduling and all those things which were not necessary. But that's again driven by the hardware, right? So if you have a disk and disk has this certain kind of spinning and stuff, using these techniques would give you better performance. Again, if you didn't know all this stuff, you could still implement everything without performance. And the thing that we worry about in operating system is to make sure that whatever operation you had, whatever disk write and read and stuff, would get you good performance as well as stuff. And probably RAID is new, right? Probably many of you didn't think about RAID unless you built your own stuff. You didn't think about RAID. And RAID is very popular, and it's becoming more and more popular because of the RAID acronym stands for Reliable Array of Inexpensive Disks, right? And inexpensive part, as time progresses, it becomes even more inexpensive. That means you probably want to think about those, right? And it's an important thing to have because if for example, you want to buy a new PC and you want to do video editing, right? what kind of RAID would you choose? Video editing, hopefully you have lots of video data, right? You have to read sequentially and you have to manipulate them, right? What kind of a disk what kind of a RAID would you use, right? Yeah.
4 or 5 so you can do parallelism, or you can take advantage of.
Yeah, or RAID 1 or whatever, right? Yeah, so I'm saying, no, those are things you'll have to wrestle with, right? So RAID 1 would give you good throughput, but it's more expensive. RAID 5 would be not so good performance, but you'll have to use less disk, right? RAID 1, you'll have to have a copy of everything. So if you have lots of money, I would choose RAID 1, right? But if you have a little bit money, I would choose RAID 5. Then you have to figure out the cost. You have to figure out the RAID controller cost, what's the cost of the disk, and all those things, right? And there's no simple answer. I mean, I think there's no simple answer. It depends on the different costs and everything, right? If you have infinite budget, I would use RAID 1, right? Because you have a copy of everything, and read is faster, write is not that slow, kind of stuff, right? But you will go make the decision a lot more than you may realize, because that's part of decision of you buying a PC or what have you, depending on what application kind of stuff, right? And ACLs and protection, right? And again, this is one thing I want to emphasize, right? There's no magic bullet in any of those stuff, right? You need to understand what is being compromised, what is not being compromised, right? So what everybody really tries to do is, you know, for a certain cost, you have a certain bunch of hardware, right? You want to get the maximum performance out of it by tweaking all these things, by caching and all those things, right? So you may see some statements like this in popular press, right? According to the Office Performance Benchmarks, Windows XP SP3 is also considerably faster than Windows Vista SP1, right? You've probably seen those stuff in popular press, right? They compare XP with Vista, XP with Mac, and all those things, right? So what does it mean when you say it's faster, right? Can you make an operating system faster than a previous version operating system? And if so, how would you make them faster? Where do you get the performance, right? Yeah.
It's better optimized for that particular use case.
Yeah, you can make it better optimized for that particular use case, right? Which usually means that it's not better optimized for the non-use case, right? It's very hard for you to make it better for all possible use cases. You can make it, so the key here is Office, right? It's faster for Office, but not faster for maybe something else, right? Maybe for games, Vista is faster or what have you, right? There is a way where you can make these things faster across the board, which is to make the operating system leaner, right? To make the scheduling decisions faster, right? To bring that down. But most operating systems you buy on the shelf have been heavily optimized already, right? So there's not a whole lot of fat left in those, right? Usually it comes with them figuring out that Office is a good application to use and optimizing for Office. So you come up with these kind of statements, right? What it means to you is, when you write programs, when you write code, you want to work with those decisions, right? If you work against it, your popular press will say, you know, blah software that you wrote is slower in Windows XP compared to Vista or something like that, right? Because you need to understand what decisions are being made, which makes Office faster, right? Because you can't make Office faster. You can only keep certain things in cache, schedule some processes differently, use some memory differently, but the underlying system is still, I mean, unless you have a different hardware, right? If you have the same exact laptop, if one operating system is running faster than the other one, that's because it's making choices which help that particular application. So if you're a developer, you like to imitate whatever Office is doing, right? So for example, like one of the things we learned was row major means the memory is laid out a certain way, right? So if you went through the column way for matrices, right? You're going against how the system is done. You'll violate all kind of caching principles. Your system will be completely slow. And there's no reason for you to do that, right? So even though mathematically going through a array row-wise or column-wise is the same, right? one of them can give you much better performance than the other one because of caching. If you knew that, then you won't do the other way. Because if you did, your manager or somebody would like probably laugh at you. They say, why would you do this? Because it's so slow, right? Does that make sense? Right? And again, that's the again, reiterate again. It has to juggle all this stuff, right? I mean, so if you had only one process that you need to run in a machine, right? How would you build that operating system? Would you change something? Would you make decisions differently than if you have to run multiple processes? Does it make life easier for you to build the operating system for one process versus multi-process kind of stuff? We'll get back to that again in a few slides, but is it easier to juggle resources for one, if a system can only run one process versus multiple, right? And many of you are nodding yes, right? Because it makes it easier to make, the less decisions I have to make, the easier it is, right? If my decision is whether I can run this process or this, I can cut down on my overhead, right? I don't have to decide. All I have to do is like, okay, there's only one, I give it all the stuff I want. Here the more I have to juggle, the more complicated it becomes. And if I make a very complex decision, if I make a very complex algorithm, then it slows down things too. So I don't want to make a complex decision, and how do you trade that off is the key, right? You will not face these things in normal programs. Like normal programs, you want to do the optimal stuff. So if you take a course in, say, algorithms, you want to come up with the optimal algorithm, right? Here you don't want the optimal algorithm. You want something which is fast enough, gets your job done, and hopefully it's good in the overall picture, right? So what about this question? If resources become plentiful, how would that affect you? So if you let's say you had a 32-core laptop processor, how would that affect your operating system? Would that change how you do stuff, or for better or worse, right? Would having 32-core or the opposite? If you had a laptop which has very scarce resources, right, very slow processor, CPU and stuff, how would these two affect your design decision? The first one, let's say you have plenty of resources, right? You have 32-core, like 64 gig of memory. So I'm not talking about systems where you need all that memory. Let's say your laptop has that much, right? How would the operating system do with these things? Yeah.
I wouldn't have to worry too much about resources. Like in most cases, just give it to them and not juggle as much.
Yeah, so when you have lots of resources and they assume a lot of resources, they're kind of a lot more liberal, right? And you may be seeing some of those in your laptops too, right? So for example, if you say you have 32 cores and you as a process had a core and you had to go to sleep or something, I don't mind giving it to you, right? I don't mind leaving it with you, right? I don't mind leaving a spin lock because I have so much resources, I don't particularly care, right? On the other hand, when you go the other way, when your resources are scarce, I have to try to make decisions which are much more optimal because there's not much, right? If I make wrong decisions here, then you will notice it, right? And many of you may have faced it, right? So if you use this, if you want to try this, don't do this on a main computer, but like pick up some old, 400, 200 megahertz, like Pentium or something, put like 8 megs of memory, try to load Vista, right? Don't do this when you are in any kind of deadline. And you'll see that it's kind of slow because Vista has, so in that machine, if you take Windows 95 and put it on that machine, it'll be fine because it's not trying, it's assuming that this is the case, right? Whereas if you put Vista, it's used to having lots of resources. It'll try to be generous, and it'll be so slow that you probably, after like a couple of hours, you'll just give up, right? But things will be slow and chugging along, right? And there are some things that we didn't stress too much, and those are stuff which are more interesting concepts, right? And that's one of the things you will probably do, it's a lifelong learning process kind of stuff, right? So when you may not learn it from a systems perspective, but you may realize it in some other sense, right? So if how many of you play PC games? So if you play PC games, so if you buy a PC for PC games, for games, right? What do you look for? I mean, obviously you'll buy the best machine possible. If you had, so if I say I give you $1 million, find a PC game, right? You're gonna come up with, you're just gonna say, give me the best of everything, right? So suppose I give you like $2,000, right? How do you decide what you want, right? What would you guys look for? How many of you bought a PC for assuming that gaming is a concern and thought about it when you made a decision? So what did you look for?
Well, you need a good video card, obviously, and like a faster processor with fewer cores is probably better since most games are not multi-threaded. Processor with more cores and slower.
Right. So the other things, if you go hardcore, you also look at the bus that you have for the card, right? So you probably heard of PCI-X versus block card, and whether it's buffered, read, or like stuff like that, right? And so essentially what you're trying to do is you're trying to send as much computation. One of the things he pointed out was most of the games don't need multiple core. So you don't want to put the money on the core. You want to put the money on the graphics card or something, right? Because that's where the processing is. Then you need to think about how to feed that piece, right? So you need to have the memory to be faster, and you need the memory to the bus to be faster, right? And essentially you're offloading the work to these kind of controllers, right? So DMA controller, graphics controller, RAID controller, or what have you, right? Each of them will do their own specific task. The challenge from an OS perspective is the more I send it off the main processor, the more I have to work with them, right? So one of the example is if I have a RAID controller which is doing something for me, or a disk controller, which means that if I have to write a block, I tell the controller I need to write a block, you do your thing, and let me know, right? Which means that when I'm trying to schedule a new process, I can't assume the work is done. So I need to. So if I kill a process, right? Earlier times, I can just take away all the memory that belonged to the process. Now, if I had another controller and it's supposed to do the I/O, I have to keep the memory locked in till that finishes before I can release this memory, right? So now we are in this weird state. We talked about processes, and we talked about creation and deletion, right? So after you delete it, in this point, there's no point for this process to exist. You're going to have to keep track of these things which were part of what the process was doing, the I/O, which hasn't finished. So I can't release all the stuff that the process was using till the I/O finished, right? But the PCBs probably have to kind of go away, because when you do a PS, you don't want to see the process exist, right? Does that make sense? The more you let somebody else do the stuff, you have to be sort of doing things. You probably realize this with the printer, right? When you have a print job, you print this, you start it in your printer, and it's gone from your application, right? But it's still printing, and you see this little process running which is doing the printing, and then it after a while it goes from your application, but it's still printing on the printer buffer, right? So at that point, if you pull the plug, sometimes if things are lost, you'll print another copy again, or it'll do something weird, right? So you run into more and more of those as you kind of outsource some of this stuff, right? You see this for disk I/O, you see that for games and stuff. The more you kind of let these things do, the operating system now has to keep track of like stuff that still is happening after it's done, kind of thing. So some of the things we learned would be kind of tweaked a little bit, right? So when the process exits, you don't really get rid of everything because you have to wait for all these things to finish. And for performance, you may leave the process sort of in the memory, but not accessible to you, right? And that's one of the reasons why when you use PowerPoint, exit, come back, it's really fast, because you internally keep all the process structures alone, leave it alone. When you exit and come back, you reuse the stuff. So you do all these things which we didn't quite talk about it explicitly, But as resources become plentiful, as you go into these kind of models, you tend to do, right? And you will have to understand what that is when you make a decision to buy for games or what have you, because how that affects your system. And if your operating system cannot deal with those, then you're in trouble, right? The other aspect which we didn't touch upon at all is reliability, right? Reliability is important to most of us. I mean, most of us don't want the machines to crash in the weirdest part. So we did talk about modules. We did talk about loading the drivers and stuff, right? So the main reason why most of the operating systems crash is not the real core operating system, but the drivers, right? How many of you had experience with the drivers failing for whatever reason, right? You see a blue screen of death all the time because of drivers, right? And if you're Microsoft, that's not a good thing because users, I'm sure after this class, you say, don't blame Microsoft, blame HP, right? Or the right thing, right? But now most normal users particularly don't care. They don't care what happened. I mean, they say, I bought this PC, I tried to print this, and it died, and you blame Microsoft or whatever, right? You can see that when people complain about like Microsoft, Windows is less stable than Mac, right? Without getting into the politics of what people say, right? How many of you thought about like how the Macs work versus the XP works in terms of the hardware control, right? Okay.
Well, Windows has taken a lot of more things into account because there's like a more general user base and more things that they're looking at, and so they have to account for a lot more things than a Mac operating system would.
So do you think that Microsoft takes care of it, or Microsoft lets you add those stuff, right? Do you think that Microsoft itself encourages or lets these things happen, or they just so happen? Because I think it's important to realize, right? Because I think one of the problems is Microsoft does not control the hardware, right? So they could say to run this operating system, you need to have this, and this hardware. But since they don't make the hardware, they have to sort of let you have whatever hardware, which means that somebody has to write the driver, and it kind of goes in, right? So I'm not convinced that Microsoft likes that model, because that's where all the problem happens, right? All the driver problem happens. And Mac being able to control the hardware throughout, right? So they can say you can only buy this hardware from us, and this hardware will only have one particular card, right? You can't buy anything else. If you have them, you can't, I mean, there's no way for you to add them to the stuff, right? So they have more control. So by virtue of that, they get more reliability, right? The other thing you notice is how many of you seen parallel ports? I have to ask that because it's kind of going away, right, for the printers, right? Fewer and fewer people, right? How many of you use serial ports? How many of you use PS2 ports, right? How many of you have seen any of those in the latest Mac, right? They don't have those, right? The Mac tries to get rid of all these stuff, right? So what's the implication of that, right? If you get rid of those, that means you have fewer drivers, fewer extra stuff, which could potentially cause these problems, right? So you get overall better reliability, right? And that's one thing which plays. So you never get anything for free, right? Reliability means that you have to have thorough control over the whole thing. And as OS stuff, if you say I won't deal with parallel ports anymore, and if you're able to execute that, you're going to get a more reliable operating system. But some people will be unhappy, kind of thing. So so I don't really believe that Windows operating system is any less technically advanced than Mac OS or what have you. But you see different behavior because of all these other decisions, which may or may not be good for you, right? Because you need to understand what is operating system's fault and what is somebody else's fault, right? And again, reiterating this because I think it's important, right? So essentially, what you're trying to do is when you do the scheduling, right? I kind of mentioned that everything is scheduling. So when you have two processes that you're running and they have to be scheduled, right? when we talked about the process module, we talked about just the CPU aspects of it, right? Like which one is going to use the most CPU in the future and all those things. But real operating systems shouldn't really look at that. They have to look at the big picture. They have to look at all the stuff. They have to figure out what's the cost of context switch, right? What's the cost of this context switch will do to TLB and all the other caches, because those come from the memory module, but you pay the price regardless. So if I want to context switch a process, I need to figure out what is a good process to run. I need to figure out what is the cost, and cost includes the cost of context switching, which is in the process module, cost of flushing the caches and stuff, which comes from the next module, the cost of losing I/O locality, which comes from the file system module, right? If you're doing a sequential access, and if halfway through if I had to context switch, then the diskette has to be moved somewhere else, and I have to do something else, right? So you have to take that into consideration, and you also have to worry about the stuff I was talking about in terms of what is being written to the disk, what is being taken out, right? In each of the modules, we talked as if the other one did not exist, right? We were talking about scheduling the disk to make it sequential and do all kind of nice stuff. But once you mix all this stuff, you have to decide all these things. Do you think the operating system can actually do a good job of mixing all these costs and come up with the right answer? I think they can't. If they did, then we'll have the perfect operating system. We'll all be using that, right? I mean, it works to the most for the most part, but there are times when these things fail, and you probably notice that when you use. So next time when you use your computer to run processes and stuff, and you're really frustrated when it's not doing what you expected, try to think of what might be happening, right? Like why is it taking so slow? Because it's doing something that you didn't want it to. And hopefully the next version they can fix that, and hopefully you can see what it would mean if you fix that, right? So sometimes the logging in time may be very slow, but the system may be very fast because of decisions they make, right? If you flip it around, then logging in may be faster, but then it'll be slow afterwards, right? So there are so many decisions that are dependent on the particular hardware, particular setup, and you have so little time to make the decision on which to schedule, right? And this is one thing we didn't explicitly state, that everything is all together. Context switch is not a process thing alone. It involves process and the memory module. It involves the file system module. It's all interlinked, and you come up with a good algorithm, right? And it's good scheduler will optimize all this stuff quickly. Right. So I mean, so these are things, food for thought when you go beyond the class, because hopefully that's the message you take away from the class. It's all about trade-off and stuff. So I would like to see how these things will affect. Let's do a kind of a thought process on different kind of systems, right? We kind of seen sort of PDA, cell phones kind of thing, desktops and servers, and how you would build an operating system for each one of those, right? So let's see, PDAs, right? How many of you have one of these things? A phone, a smartphone, or iPhone, or this is a wristwatch Linux machine. I have no idea why you would run Linux on a wristwatch, but you could, right? So you have all these things, right? And one of the things you may notice is they tend to become more powerful as time goes on, right? I mean, I think iPhone is practically there as a sort of like a laptop for some of the tasks, right? Some of the features you notice with them they're inexpensive, right? You may not agree that iPhone at $400 is inexpensive, but compared to the laptops, they're inexpensive, right? And they all have constraints of CPU and memory, storage, and screen, right? The processor may be faster now and all those things, but they're under very tight constraints, right? So tomorrow, if you come up with something which will make some of these things go really fast, let's say you make this processor go at 800 megahertz or something, right? This area of hardware, you would then decide to make this thing smaller, right? So if you ask me, would you want a new iPhone which is twice as fast in the CPU or twice as small in terms of size, right? Up to a certain point, you want the smaller size kind of thing, right? So the same thing which works in laptops, where the processor kind of doubles every so often, does not really work here, because if you get a better processor, you also try to make it smaller, right? In laptops, you kind of get stuck with, I mean, nobody's talking about a 1-inch laptop. You don't want to reduce the size, because 15-inch or so is kind of considered to be universally acceptable. So if you look at the 15-inch laptops from 95 to now, they're becoming like faster and faster in like every indicator, right? And these things don't get to be like that because these are small, inexpensive. So you would like to make them more inexpensive than to make them faster, right? Because people are not running like massive services on those. And there's a whole bunch of operating systems on these, right? Like Symbian, Palm OS, Mac OS, and Linux, and all those things, right? So let's think about what. So they're running operating system, right? They're running an operating system that we kind of talked about. One of the things you may notice is they are usually running only one application, right? By the virtue of these little screens, it's usually not possible to run multiple applications, right? Even though more of them are trying to run those, you don't really want to run. This will need to run like PowerPoint and Word and all those things inside this little screen, right? So sometimes what they do is they freeze the application when they switch. Palm used to do that. So essentially, it looks like you're running multiple applications. So when you switch from one application to another application, it freezes everything into storage and then runs other one, right? So it's not running multiple applications. It's basically completely freezing one and then starting the other one, right? So since you're only running one application, right, things become a lot easier, right? For example, there's no process synchronization because two processes cannot run at the same time. So you don't have to worry about, it's only between your application. There's no other application, right? And this is one of the things you begin to notice. Like most of them tend to have multimedia, like video playback. Like let's take iPhone, right? It can play video, and it doesn't play video by using the main CPU. It has hardware to do that. So it sort of uses these other stuff to do the work. So if you want to play video, it lets the video to a separate chip kind of thing, right? But other than that, it's not very high performance, right? So you have to make the same sort of decisions that you make in regular file systems, in regular operating systems. But these constraints let you choose different policies, right? Does that sort of make sense? Well, and also they don't have MMUs because they're so small. So you don't think about virtual memory because these are so small. You can't swap in and out because those things are so small. They're so energy constrained. So you end up with only one memory model, and you get some of the benefits we talked about, but a lot of things can be thrown out, right? I think I have a picture on. And the notion of security and all those things become a lot easier because I don't have to worry about security on a PDA because you hope it's this physical security, right? So this is the sort of the figure that Apple has for iPhone, right? This is the sort of the figure they have for the regular desktop Mac, right? So if you notice, there is, I don't know if you can see from the back, right? There's this Darwin, which is supposed to be the operating system. And then there's these libraries which together give you the whole package that you buy, right? So up here on the user experience, you have the notion of a windowing system called Aqua and Spotlight and so on and so forth. And then you have the programming aspects, Cocoa, Java, what have you. And the graphics library which make these things happen. And then there's the operating system, right? If you look over here, right, on the iPhone, you have the core OS, which is supposedly like this, right? Which is the same as here. And then core services, which is sort of these graphics libraries. And media playback, which is sort of like, I guess the same thing here. And then the interface, which is Cocoa Touch, which is basically the touch-based stuff, right? So what would you do in terms of moving the operating system from here to here? Can you have the same operating system to do both this stuff? how would you port this operating system to here? Would you have different abstractions? Would you throw away some abstractions because it does not make sense? Would you make different decisions for scheduling, or all of them, or I mean, I'm using Apple here, but if you think of Microsoft, you have the Windows XP and then the Windows Mobile, right? How many of you have Windows Mobile, cell phone, or PDA sort of things? How many of you have? Oh, one. Wow. I thought they had a much bigger market share. How many of you had like iPhone sort of things?
We're all very poor.
But the demographic that they're all fighting for is you guys, right? It's like I think the iPhone is like really trying for reaching for younger audience than the older audience, right? So anyway, so if you ever see those in stores, or probably buy them after a summer job or something, right? So thinking about what would you do, right? Like how would you? Is it possible? So can they make the claim that iPhone uses Mac OS? They're making the claim, right? What does it mean? What does it mean when they say it's providing those services? How much truth there is and how much of it is untrue, right? Why are they able to make that claim that they're running? Clearly, I mean, like the laptop thing, it's really huge and all those things, right? What is common between these two that allows them to make the claim? So in terms of like, yeah, sorry.
It's like some of the API calls and like external interfaces that developers would interface to could look the same.
Mm-hmm. Yeah, so as long as these things look similar to you, you'll be fine, right? Like so. Here the interface is different. Obviously there's no keyboard, so they can get rid of the keyboard kind of components. But as long as it sort of looks the same, you can kind of say the same thing, right? So in terms of abstractions, right? Do you think they provide like the process abstraction in both these things? Do you think it's hard to provide a process abstraction on a small device versus a large device? It probably is not, right? Because process, if you think about it, was not that complicated. I mean, you need to have a notion of a process control block, and essentially it's a running program kind of thing. So they may still have the notion of a fork and process and all the things we learned in class, right? Fork, process, and all those things. The main difference comes in the things we didn't learn in class, right? Which is the notion of the touch UI or the screen, a keyboard, mouse, and all those things, right? So they can get rid of all those things because they don't even make sense for you to use, right? There's no point in having a keyboard interface to your iPhone when there's no keyboard, right? So the core operating system is really small, right? So when you think of Windows XP, you barely, like whatever we studied in class, I bet you never have to deal with those, right? There's very little of the file system, there's very little of the memory stuff, there's very little of the process threading model. The bulk of the stuff you see is the stuff up here, the windowing stuff and the libraries and Win32 API and all those things, right? Most of the time it's a lot easier to move just this little operating system, right? Which may be one area where you had an opinion before you came to class and now, right? If you thought of this as the operating system, throughout the class all we studied was this, right? We didn't look at all about any of this stuff, right? So the operating system itself may be moved back and forth here because that's very small functionality, right? The whole other stuff is the what you interact with. And as long as they can move that, they can make the claim because it still has the process, it still has the memory and all those things. It does not have maybe virtual memory, but you're not supposed to know about that anyway, because if you write a C program, they should work in both the cases. So it can be an operating system in the technical sense, not in the sense of what users are used to, because you can't put your Mac operating system and run on this little iPhone. But truthfully, they can do both, right? Is that sort of make sense? I'm sort of rushing through because unfortunately we don't have too much time left in the class, right? So thinking of the next set of machines, right, which is the laptops, and laptops are becoming pretty popular, right? We are doing some study, and most of our campus seems to use laptops. At least the students seem to use laptops, right? I think we have like about 12,500 or 13,000 wireless devices active. And the dormitories seem to have like 1,000 or so desktops, right? So it used to be the other way, like 2 years back. So most of us are using laptops. So let's look at the laptop class machines, right? They are much faster than what they were a few years back, right? How many of you still use desktops? How many of you are exclusively laptops? Laptops? Okay, so I'm guessing how many desktops? Okay, so practically everybody sort of moved to the laptop model, right? And they're much there's really not that much reason why you want to have desktop, right? I mean, unless you want something which the normal laptops can do. They're dual core, have like 4 gigs of memory and 320 gigs of hard drive, and pretty soon we'll have pretty big chunks of flash drive, SSD drive, right? I think they're supposed to come up with 512 gigs by 2009, which is not that far off, right? So you'll have much faster and all those things, right? But does that mean that the laptop and the desktop computers will have are the same? Would you make decisions differently because you're a laptop than you are a desktop? Hey, somebody said yes. Yeah.
Probably want to save more power on a laptop.
Yeah. So yes, power is a massive thing. So for people who have laptops, you realize that the battery is always running out, right? So you want to be aware of those. So you want to make decisions based on power, right? And many of you have seen, like, the operating system lets you run at a high performance and a low performance, depending on whether it's powered or not. And that comes into the play regardless of how much resources the laptop have, right? Many of you may realize that if you have a laptop and you run it fully on capacity, right? Write a small loop which uses the whole CPU and all the memory and all those things, right? Your laptops become hot, right? Like, they're no longer laptop, right? If you keep them in your lap, it probably burns you, right? So you have to worry about those concerns which we didn't address in this class, but they become apparent quite easily, right? If I use all the CPU, then your machine gets very hot, and the fan kicks in and it becomes so loud. It's not really, people don't like that, right? People don't like if the CPU, the processor, the laptop becomes very loud. So you have to take that into scheduling constraint, right? So I have to choose different processes in order not to make it super hot, because then I have to run the fan, and it's not a thing that people like, right? And the other part is the buffer, using buffers for performance. It takes an interesting role here, right? I would rather not write often to the disk, because then I can save energy by storing them in buffers, right? But these are laptops, right? So if you ever have to pull the power out, I may lose the power. I may run into trouble. But then there's a battery, right? So compared to desktops, it's not likely that somebody would pull the plug immediately. So I have to decide whether I should use lots of buffer, knowing that there's a battery which will hopefully help me flush the stuff out, right? So that's a decision you have to do, right? You have to decide whether you want to keep them in buffer compared to desktops where you're supposed to have a UPS, but many of you may not have a UPS, right? Whereas laptops, you tend to have a battery backup, so maybe I can help that. But that's a decision they always wrestle with, how much buffer to use and stuff, because reliability come into the play. And security-wise, it's still the case that it's assumed that laptops are always with you and you don't do the stuff. I'm going to quickly talk a little bit about servers. And when you talk about servers, right? So you see, I don't know if you can see the picture on the screen, but essentially you have racks of servers and thousands of them in a room kind of stuff, right? You run an operating system here, and most of the time there is no user interface, there's no screen or whatever. These are all running just processes. The decisions you make on the server, when you think about it, are a lot different than what you do on the desktop, because here throughput is more important, not user screens and stuff. So you still have the same things we learned, but you tweak them in different ways to get the different environment, right? Yeah, that's we're out of time, but just think about all the things that you would do. So all the things we studied, when you go to different setup, you kind of tweak a little bit to make them fit there. But see you on Monday.